Welcome to STEAM Cafe. We do this every third Tuesday. STEAM Cafe is a partnership with South Dakota Public Broadcasting and Hay Camp. We couldn't do it without them, and we couldn't do it without you, so thank you for coming. Those of you who are attending online, thank you for coming as well. At the very end, we will have a Q&A with our presenter. Those of you who are attending online can ask your question either in the chat box or in the Q&A, and we will make sure it gets answered live tonight. So tonight I would like to introduce our presenter, Dr. Jaret Heise, who is the Science Director at the Sanford Underground Research Facility.
Testing, testing, testing. All right, very good. Well, thank you for the introduction. Thanks for inviting me to share what I think are some exciting times up at the lab and lead, and I'm hoping to convince you of the same. So as introduced, my name is Jaret Heise. I'm the Science Director. I've been doing underground science now for, 25 years almost. And I've been up at the lab now for 15 years. And for those of you who have followed our path from where we started to where we are right now, you can appreciate that we've seen a few changes over the years, but it's been a fun ride, and I'm hoping to share a little bit of that excitement here tonight. All right. So for thousands of years, actually hundreds of thousands of years, humanity has been looking up at the stars, seeking to learn what secrets they hold and to understand our place in the universe. Our observations have produced some big questions, including what is the universe made of? And so that's really the foundation for and the motivation for the science that we do, especially the physics science at SURF. So it turns out that the stuff that we know and love, the normal matter in the universe, the tables, the chairs, the planets, stars, galaxies, the beer, it's all made of normal matter, so electrons, quarks, making protons and neutrons. That constitutes a whopping 4% of the universe. And so just in that statement alone, that's both humbling and really terribly exciting, because there's so much more that we don't understand that scientists have the opportunity to go and find. And so instead of calling this the known universe, it's probably better to call it the unknown universe. There are 5 times the amount of matter in the universe in a form that we have no idea what it is. We call it dark matter to hide our ignorance, but there's a lot of compelling evidence that this type of matter exists in the universe, from the rotation speeds of galaxies to light bending around matter that we can't see, gravitational lensing. So 5 times this blue slice is in that dark matter. The majority of that orange chart is in the form of dark energy. Dark energy was discovered about 20 years ago, and it results from the accelerating expansion of the universe. The universe, when I was going to school, we thought of the Big Crunch. So you have the Big Bang and you have the Big Crunch. We don't think that anymore, because when we look at the universe, it's not slowing down, it's speeding up. That expansion is speeding up. And that's, like I said, a discovery that was only found in the last 20, 25 years. And that blew our minds. And that's another part of this unknown universe that we're happy to try to explore. So as you look at this chart, you see what we think we know, what we know, and what we don't know. And so as you can see, it's a tremendously exciting time to be a scientist when there's so much of the universe waiting to be discovered. Now, I probably oversold it a bit by saying that we understand even this 4% of the universe. Take the neutrino. It's the strangest particle that we've ever discovered. It was invented in the 1930s. It was first discovered in the 1950s. And after 65 years, we still don't know how much it weighs. Having said that, it's one of its other properties is it's very hard to detect. And by very hard to detect, let's give you an idea of how rarely it interacts. So you can go to Walmart and you buy 6 trillion light years of lead, 6 million light years of lead, and half of the neutrinos will make it through off the other side. Actually, I take that back. 6 trillion miles, not light years. It's 6 light years. So it doesn't matter. 6 trillion of anything is a unfathomably hard number to grasp. So all of that lead, trillions of miles of lead, half of them will make it through to the other side. Neutrinos come from just about everything. They come from the Earth in the natural uranium, thorium, and potassium. They come from particle accelerators. They come from bananas. The average banana has maybe 12 neutrinos decaying or given off every second. People give off neutrinos because of the potassium in your body, because of the bananas you eat, among other things. There, you're giving off about 1,000 neutrinos every second. The neutrinos coming from the sun are by far the most abundant source. And so if I hold out my hand, so we're getting this trillion a couple times, more than 1 trillion neutrinos are going through my hand every second. We don't feel them. In fact, if you had 1 neutrino interact in your body in your lifetime, you should go buy a lottery ticket, because that's about the extent of which these neutrinos are going to interact with you. And there's trillions going through your hand every second. So I'll go back to the statement I made at the opening of this particular slide. This is the strangest particle we've ever encountered, but we think it holds the key to a lot of really exciting science. But before I get into that, I do want to emphasize or mention that it comes in 3 types: the electron, muon, and tau type. And the fact that it can change from one type into another is just another in this long list of bizarre properties of the neutrino. And there have been some important discoveries related to that. In fact, we know that the neutrino has mass because of the fact that it can change from one type into another. If it didn't have mass, it could not do that. And so why does the neutrino, what does the neutrino weigh? I mentioned already that we don't know how much it weighs. We have limits. We know it's very, 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 very light. It's over 1 million times lighter than the electron, which is already the lightest fundamental particle that we know of. Why is it so light? You may have heard of the Higgs boson. Well, the Higgs boson sort of interacts with, or presents this field, and matter interacts with it. And that different interaction manifests itself as the mass of particles in different ways. The neutrino is so much different, so much lighter than the other particles. We don't know why that is. And so maybe it has a special relationship with the Higgs particle. And then the ultimate question at the bottom here is really what's motivating one of our flagship experiments in the US, the LBNF DUNE project, exploring matter-antimatter asymmetry. So just to reiterate or convince you that along the timeline, along the life of the neutrino as we know it so far, from its invention in the 1930s up through today, the tidbits of information that we've gathered about the neutrino, discoveries of the different flavors, for instance, have all led to Nobel Prizes. So there's a number of Nobel Prizes sprinkled along this timeline, and we fully anticipate that the science that is coming out of SURF in the future will generate at least one more Nobel Prize with some of the science that I'll be telling you about tonight. So very exciting, very important research. So getting back to that matter-antimatter asymmetry, at the time of the Big Bang, there were equal parts matter and antimatter produced. And if you remember your Star Trek physics, when antimatter and matter collide, they produce energy, they produce light. But that's not the universe that we see today. When you look out into the stars and into the universe, you see stars, you see galaxies, you see tables, chairs, planets, stars. That's not light. And so you could take this question and maybe turn it into something more existential. With the matter-antimatter asymmetry that produced the universe that we see, we shouldn't exist given the fact that the Big Bang produced equal parts. So why do we exist? Based on the science that we expect from the Big Bang, why do we exist? Why isn't the universe filled with light, with energy? Because it isn't. So there has to be something that gives us the universe we see today. And so one way of describing how subtle that changes is if you had equal parts matter and antimatter at the Big Bang, 1 part in a billion would be all that you need to change in order to give the universe that we see today. And we think that the neutrino has that secret of nature preferring to decay into or react to give slightly more matter than antimatter. 1 part in a billion in terms of an asymmetry in that interaction, that preference, is all you need with the neutrino to give you the universe that we see today that's full of matter and almost no antimatter. Alrighty, so with that motivation behind us, we have to motivate where we start looking for some of these rare process events, neutrino properties, dark matter, that 5 times more matter than normal matter. And so we go underground. And so why do we go underground? Let's see if I can get this going here. Yep. On the surface of the Earth, we're constantly bombarded by cosmic ray muons. You hold out your hand, 1 or 2 are going through your hand every second. And that's illustrated by that rain that's falling down in the animation. If you have a mile of rock as a filter, you don't get 0, but you reduce that number by about a factor of 10 million. So 2 or 3 on the surface translates into 1 a month underground. And if you're looking for rare physics processes, looking for neutrino interactions, looking for evidence of dark matter, you need to give yourself every advantage, and you need the quietest environment that you can find to do those searches, to gather that data. And that's what the 48, 50-foot level of surf offers to these physics experiments. The quiet environment to look for these really, really quiet processes. Alrighty. Before we dive into the science, I wanted to put things into a global perspective. Sprinkled around the globe, there are 18 underground labs leveraging exactly the same shielding advantage that I illustrated in the animation in the previous slide. This group probably doesn't need to ask the question, where is surf? You're probably fairly familiar, 45 minutes, get on the highway and head up north. But you can see all of the other laboratories that are in this game with us, sprinkled around in Europe. There's quite a few. In Asia, there's a few labs here. One opened very recently in Australia, the gold mine Stahl. There are others that are waiting for funding from their federal governments in India and in South America, in Andes. And of course, surf here in South Dakota is what we're going to be talking about mostly today, but we'll be doing some compare and contrast just to give you a sense of how our facility stacks up against the entire world. One way of looking at what a world-class underground facility can provide the underground science community is the depth. For the physics experiments, that screening power to create a quiet environment in the underground to do these searches is governed by the muon flux. So how many of these nuisance background events are going to visit your underground laboratory? And that's what this axis is. But basically, the further down on this plot, closer to the floor, means deep. The deeper, the better the shielding. So you can see the labs here in North America, in Europe, Asia, and the Southern Hemisphere. Focusing on surf for a second, the dark circle is what we currently have for laboratory space. We have 2 campuses, the Ross and the Davis campus on the 48, 50-foot level, and I'll show you a little bit more about those here in a second. The slightly darker circle surrounding that is the expansion for the LBNF Dune project associated with exploring that matter-antimatter asymmetry. And then the slightly lighter circle surrounding that is the expansion that we're hoping to embark on next year, and we'll talk a little bit more about that as well. We've also, surf, given the 125 years of mining history, has a huge footprint, has an immense potential for developing underground space, all the way from the surface to the 8,000-foot level. One of the sites proposed earlier in our history was on the 7,400-foot level, and that's shown here. And with its expected rock shielding power, it would be the deepest laboratory anywhere in the world. Even deeper than the one here in China. Another really big lab is Italy, and then up in Canada, Snow Lab is actually the very deepest at the moment, inching out the Chinese lab. So a lot of the motivation for the expansion can be shown and summarized in this plot. A deep lab, so a lot of these smaller labs are fairly shallow. This one in Japan for Hyper-K is quite shallow. And that limits the science, that limits the physics you can do. And so a deeper site like the one at SURF and possible expansions serves the underground science community better than a lot of these other ones can. All right, so going from that global perspective, let's home in on Leeds, South Dakota. Here's an aerial view showing the SURF site. We're the nation's deepest and only underground lab really right now, promoting transformational and compelling science in a host of disciplines, not just physics, although I'll be focusing a lot on physics today. We do offer unique attributes in our facility for the biology, geology, and engineering community as well. So we've been open as a lab now since summer of 2007. That puts us over 15 years in this business. And that's not to mention that the rich history that we had before, which was the Ray Davis work, where we scrolled through it very quickly on the Nobel Prize slide, but Ray Davis shared in a Nobel Prize for his work starting in the mid-1960s that led ultimately to understanding that neutrinos oscillate, that they can change from one type into another. And so that work was pioneering, it was seminal, it was extremely important for the understanding and motivating the LBNF Dune project that we have going on that's being built at our facility today. Huge amount of support from the state of South Dakota. Also an important donation from Homestake Barrack for the site. We have an important donation from T. Denny Sanford. His gift of $70 million was really instrumental in getting our facility off the ground and on the map and to receive the federal funding that it does today. But I want to call out once again the strong support by the state of South Dakota. Up until a couple months ago, that was tallied at around $62 million for a state of 800,000 people, 850,000 people. That's immense, that's huge. That's visionary, that's investing in our future. And then with the recent appropriation, and I'll come back to this, of $13 million for our expansion, that was extremely, that was wonderful. It was wonderful support. We are currently funded directly through the Department of Energy. Federal dollars come to support our operations and some infrastructure improvement projects. And so we are very, very, very happy for that, to the tune of $35 million a year. A couple of features to point out on this plot. There's two main complexes, the Yates complex and the Ross complex. Each of those has a head frame and hoist system that will go down to roughly the 5,000 foot level. We have a recent building funded through state funds as well, named after Governor Rounds, who has been a huge champion for our project over the many years, both as governor and as a senator. In fact, I'm traveling to DC tomorrow for an event that he sponsored, and we are extremely supportive of his vision in this area. So those two complexes, there's a recent addition. If you've been up to Lead in the not too distant past, you'll notice a conveyor system that goes across Highway 85. That's for moving the rock excavated from the underground into a very convenient repository for 800,000 tons of rock. And if you think that we have any chance of filling that open cut up, not a hope. 800,000 tons of rock sounds like a lot. When I show you the caverns, you're going to say, oh my goodness, those are huge, and they are. 800,000 tons of rock is less than 1% of the volume of the open cut. It's a truly immense feature in the Lead area. All right, a couple other pictures. The two head frames, the Ross and the Yates, actually looking toward the open cut from the south. So a nice picture showing that infrastructure, the hoisting buildings off to the side, our main administration building with the Yates shaft in the background. The new Rounds Operations Center replaces the machine shop that was used for homestake purposes during mining. Looks very similar, but completely redone. with offices for some of our operations and engineering staff, a warehouse, and a shop, a maintenance shop. Across the street is a surface laboratory where some of the dark matter experiments I'll be showing you were constructed. And then some of the amazingly huge and impressive hoist room equipment. So if we look at the real estate or property sort of end on, there's 7 main elevations that are dedicated for science. Starting near the surface, we have the 300-foot level all the way down to the 4850-foot level. We'll be focusing on that mile deep site. But you can see that there are other elevations, and other disciplines take advantage of these sites. Not everyone's looking for the highest amount of shielding from cosmic ray muons. That doesn't bother the geologists, right? They're looking for the geology. They're not looking necessarily for the cosmic rays that are impacting the science that the physicists are doing. Total of 400 miles, 600 kilometers of tunnels, top to bottom. So a huge amount of real estate that can be developed to serve science. Right now, 29 elevations are accessible, and I mentioned just a subset are set aside for science, and there's lots of good reasons for that. These circles in red show past and present experiment sites. Many of them are the smaller biology, geology sites, but they've taken good advantage of our footprint over the years. A couple other things to point out are 2 main shafts, once again, the Ross and the Yates, and then 2 main ventilation shafts. The ventilation in the underground workings is extremely important, so didn't want to forget those. All right, so focusing now on the 4850-foot level, once again, the Yates and Ross shafts, the Davis campus housing our main physics experiments currently operating is at the base of the Yates shaft at the Davis campus. Over at the base of the Ross shaft in blue is the Ross campus that's currently, operations are currently suspended there because of the elephant in the room, if you want to think of it that way, a colossus here being constructed. And so we opted to shut down operations there so that they wouldn't be interrupted by the construction and then removal, the drill and blast of 800,000 tons of rock. So we'll talk a little bit about what's going on at the Davis campus and also factor in some of the science that we hope to resume at the Ross campus next year. But just while we're on this slide, and you can see the 2 campuses here in blue, if you remember that plot, the circles I had of the underground labs around the world, that small circle is represented by these 2 campuses. And then the larger circle, if you remember, is this expansion. This is 5 times the footprint and 25 times the volume of the currently existing footprint for science that will be developed with the LBNF Dune experiment. Some pictures, since we can't take you underground for a tour, but we wanted to nonetheless show you what things look like underground. This is some of the science space at the Davis campus that was before they moved in all of the scientific equipment, so you can see what the facility offers. And so this is a space that's being used to explore neutrino properties with the Majorana demonstrator. This has been used for a succession of dark matter experiments, first Lux and then LZ, and they use this large shielding tank filled with water to help shield the natural radiation in the space. The Davis campus all in is about 30,000 square feet. For the science space itself is about 10,000 square feet, and then you can do the arithmetic if you want to look at the exact volumes and footprints of these spaces, but a decent size space. But as we'll touch on later in the presentation, as big as this space is for the science that you'll be hearing about today, it's not big enough for the next generation of experiments that are coming down the pipe, looking for neutrinos, looking for dark matter. They need a larger space to increase the sensitivity beyond where the state of the art is today. All right, our science program, I'm just going to touch on this and then focus a little bit on the main physics experiments, but it does involve various flavors of physics, dark matter, remember 5 times more dark matter than normal matter, properties of neutrinos today with the Majorana demonstrator using almost 50 kilograms of germanium to look for a rare nuclear decay. And then in our future LBNF Dune, We also accommodate biologists who come underground and search for either new forms of life, life that can live inside rock, and School of Mines in particular has had a number of folks that are interested in commercializing, discovering new organisms and figuring out how they can be applied to, say, catalyze the biofuel production using corn stover. Those types of applications are supported by our underground facility and faculty at School of Mines and other places, institutions throughout the state. Another one I want to quickly highlight here is geothermal. It's been a big Department of Energy initiative, and you see here an installation on the 4,100-foot level, so one of those other elevations, not on the 4,850-foot level. 9 national labs, a collaboration of over 120 researchers looking to study and optimize how enhanced geothermal systems can recover heat from rock. Not that we're going to set up a geothermal energy source at surf and heat people's homes, but it's doing the R&D that can contribute to that technology future on an industrial scale. The science program has attracted researchers from all over the world. Right now we have 30 experiments, many in the physics category, more than half a dozen biologists, maybe half a dozen geology, also engineering, but I won't say too much about that. But 2,000 collaborators, not necessarily coming to surf, but back at their home institutions, analyzing the data that comes from surf, 200 institutions in 38 countries. For the folks that are coming on site on a regular basis, that number is almost 400 over the last couple years. And all time since we opened as a laboratory in 2007, we're getting up past 700, maybe 750 researchers who travel to this area. They stay in hotels, they go to the local pubs, they drink beer, just like the rest of us, and more to come for sure. A large part of this collaborator number is on the Dune collaboration, the LBNF Dune collaboration. Those scientists will start coming here in bigger numbers than they have been so far. Once the caverns are built and the detectors are operational, that will be a big contingent. Alrighty. Another way to look at that is over time. You can see our science, general science groups, sort of the non-LBNF Dune, shown in green, from when we opened as a laboratory in the summer of '07 through this month, or last month actually, May. A couple features are shown here in the black squares where we represent the number of groups that are on site in a given month. So onesie twosies early in our operation as a laboratory, and then up to maybe now about a dozen with some scatter around that. You can see the effect of COVID here in the spring of 2020, where we didn't shut down completely. We went to essential operations, but it was a big dip in the level of effort on the science side. The blue is the LBNF Dune. Not so much scientists these days, but the excavation contractors developing the large spaces that will accommodate the big detectors. And you can see that those numbers really are a huge number compared to the scientists that we've had and accommodated so far. So a big sea change in the level of activity at our site since 2016, but mostly since 2019, late 2019. Already, a whirlwind tour of our 3 main physics experiments that are currently operating. Lux Zeppelin uses 10 tons of xenon to search for dark matter. They published a result last summer. Big splash was actually right around July 4th. They are the most sensitive dark matter experiment looking for WIMPs anywhere in the world. So right here in South Dakota, 45 minutes away. They are continuing to collect data. They'll collect data into 2026, 27, somewhere in there. The Majorana demonstrator is looking for properties of neutrinos by exploring a rare decay called neutrinoless double beta decay, using almost 50 kilograms of germanium. These silver hockey pucks may be a little hard to see, but these are the germanium crystals. And some of them are enriched in a certain isotope that make them more sensitive and susceptible to this rare decay that no one's ever seen. At one point, these were about $6,000 an ounce enriched germanium, so 2 or 3 times the price of gold. They came from Russia. That's not going to be a good option going forward, and there are other sources in the world for this isotopically enriched material. They published their final results last summer, around the same time as LZ, and now they switched gears. They're looking for a rare decay of an element called tantalum, and they've published some results just recently and have submitted that publication to one of the most prestigious journals in physics. Finally here, Casper, doing some nuclear astrophysics. They were mothballed because they were operating at the Ross campus. They're going to come back online in 2024. And you can see this particle accelerator, maybe 40, 50 feet in length, a little different than the LHC that you may be familiar with in CERN. So that is 90,000 feet. This is 40 feet. That doesn't mean that you can't still do very good physics with a short accelerator. They're looking for processes that occur inside stars in our sun, whereas the LHC is looking for processes that took place shortly after the Big Bang. So different energy scales, but it's still valuable. That this science has not been done and needs to be explored with this accelerator. So as I mentioned, starting up next year. We're going to read each and every single one of these papers tonight. No, we're not. So this is a list of high impact, not all of the publications that come out of the science at our facility, but these are the highest impact ones. Early on in our life, a lot of the biologists submitting to Nature, that level of publication, and then the physics experiments, first with the smaller Lux experiment looking for dark matter with 1/3 of a ton of xenon, then moving on to LZ more recently with 10 tons of xenon. And then in the middle, there's a Casper publication. There's some Majorana, a rich science suite from Majorana. So basically one high impact publication per year of our operation, if you want to think of it in those terms. I wanted to quickly touch on, since we've just reviewed basic science, looking for dark matter, neutrinos, properties of reactions that take place inside stars, scientists are super pumped about understanding that those reactions, that science, help us understand how the universe works. But maybe not everyone in this audience has that as their main motivation. So what are the applications? That's a question I often get in presentations. And we won't go into all of these in much detail, but the science from high energy physics and nuclear physics shows up in a host of applications, from advanced manufacturing, e-beam welding. The food industry uses a lot of radiation techniques, medical imaging, MRIs, CAT scans, all that technology. Computing, not to mention that CERN and scientists at CERN helped create the World Wide Web to communicate with scientists over large collaborations. Quantum computing, and in fact, quantum computing would benefit from going underground the same way that the physics experiment benefit. The shielding from the cosmic ray rain will help the quantum computing sector. GPS came out of general relativity and the science that goes into understanding how weak interactions and the forces of nature work. And the list goes on. Non-proliferation is another one. If you had asked maybe 20 years ago, that neutrino that goes through 6 million miles of lead, what are we going to use it for? It's going to be an energy source. That's the first thing I always get asked. Well, if you can barely see it and it doesn't weigh very much, chances are it's not going to be much of an energy source. But because you can't stop it, you can monitor what's going on in the nuclear reactors of countries that you don't think are maybe friendly to the United States or others in the Western club. And so being able to monitor for that non-proliferation, put small neutrino detectors at border crossings. These are all happening today, whereas when I was a grad student many years ago, I don't know. I don't know what a neutrino is good for, but people come up with good ideas, and sure enough, there are lots of good ideas for how to use neutrinos. For dark matter, that's a harder question. First, we have to discover it, and then we'll probably not turn it into an energy source, but who knows? Alrighty, on to the LB&F dune. How am I doing for time? Getting there. So this is the flagship high energy physics flagship funded by the Department of Energy. This is shooting a beam of neutrinos from Fermilab in Chicago through the Earth. There's no pipe. The neutrinos, as we talked about, 6 million miles of lead, not going to stop neutrinos with just 800 miles of Earth. So shoot from an accelerator in Illinois and capture them in large detectors. 13 million gallons of liquid argon, large detectors. That's what we're looking to build in South Dakota. So the LBNF Dune project has a very solid physics motivation, looking for the matter-antimatter asymmetry. If there's a massive star that explodes in our galaxy and even in the next galaxy over, we will see that stream of neutrinos and understand more about the mechanisms that produce these massive explosions. And then finally, unification of forces, looking for proton decay and other rare decays that no one has seen after decades of searching that will help us understand the forces of nature and how they might combine at higher energies. All right, I have a video here that tells you a bit more about what's going on with LBNF Dune. There's some background music, but you don't need to listen too carefully, but it gives you some ambiance. So the efforts, because of the location on the 4850-foot level near the Ross shaft, all of the logistics are through the Ross shaft. We showed you that there's more to the 4850-foot level than just LBNF, but this focuses in on what is being developed. And the unit of area is the soccer pitch. This is an international project, and so we want to have a calibrated sports analogy that the international community will understand. So these caverns in total, almost 500 feet long, 8-story tall, 65 feet wide. In these caverns, we're going to install big thermoses, big cooler chests. And that's what this crisscross of red beams is, the exoskeleton for a huge cooler, each of which will have 3 million gallons of liquid argon. That steel for each one of those is about 6 million pounds of steel just for the container. And that isn't the technology, the detector that goes into it. So a huge, just an immense, humongous project to consider. Building it underground, building a ship in a bottle, literally. So yeah, minus 300 Fahrenheit is what these detectors need to be cooled to. So a lot of cryogenic systems will be brought to bear on this experiment. All right. So here's that in schematic view, the Ross shaft and the new development for the LBNF Dune project. 2 large chambers up to almost 500 feet long, 8-story tall building. There's 2 of those, a slightly longer utility cavern in the center. The beam of neutrinos from Fermilab is coming from the east, as you might expect. First detector will be installed in a corner of half of the north cavern. Second detector in the south cavern, and then they'll still looking for the final funding for the last 2 of these detectors on the order of $100 or $200 million each. CERN has provided the detectors for these first 2 as a very significant international contribution. Some progress. This was hot off the presses as of yesterday morning. Basically, the bottom line is just under 70% complete in terms of the volume of rock that's been drilled and blasted. And another way of looking at that that's maybe a bit more intuitive is if you look at the cross-section of each of these caverns, the central utility cavern is complete. There's no more excavation required to build that one out. Now the concrete floor and some of the outfitting will begin next year. These ones are still in progress. The north cavern here is the furthest advanced, maybe about 70% complete. This one's a little less, maybe 40% complete. What you see in these squares is how they do the drill and blast. It's called benching. So you first do the pilot drift, then you blast out a larger cut and then go to the full width. And then you drill into the floor, blast that, remove that waste rock, and do that over and over and over again as you go down, 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 down. Speaking of drill and blast, let's see what that sounds like. maybe a little less dramatic than you might have been expecting, but they do that thousands of times to break up the rock and then hoist that rock to ultimately in the open cut. Here's some pictures of the massive equipment. These bolters are the biggest bolters in North America, coming to do work in Lead to build the LBNF facility. And so you can see a couple of them in action here. This is probably in the North Cavern. You can also see some beams. There'll be a hoisting system, a bridge crane, and then a monorail in the center. These are protected while the drill and blast is going on. And then here's a little further down as they're benching, so making the cavern taller. You can see some of the blasted rock at the bottom here. You can see the beams for the hoisting systems, those are uncovered, and more work to do in that North Cavern. This is an interesting picture, mostly because of the scale. So once again, the largest mining equipment, these drillers and bolters are the biggest anywhere in North America, going up to the top. But the real scale here is the guy who does the maintenance on this down at the bottom there. So huge pieces of equipment. And there's the open cut. That's where the rock is going. Like I said, less than 1% of the 800,000 tons of rock. You'll be lucky. This is a view that most of the public doesn't get to see, and so you can see a little bit of some of the debris going in there, but it'll be very hard to even see that 800,000 tons. Literally a drop in the bucket. Alrighty, looking to our future as we wrap up, the United States right now is in a strategic planning mode. So high energy physics goes to the underground science community every 7 years or thereabouts and says, tell us what the highest priority science is in the world and in the US in particular. That community gets together and says, here are our top priorities. They give that information into a report, hand that report over to another committee that then prioritizes it based on cost and schedule. That community input is complete. Underground space was identified in that process. We need more underground space to meet the needs of the next generation of experiments that the US wants to lead. And we went to that community planning meeting with a pitch saying, we want to build more space underground. And the community says, yes, please. And we took that to the prioritization panel that's ongoing right now. We pitched that to the state legislatures, and we made a really strong case early in the session. And as of March, we were appropriated $13 million, which was amazing. I alluded to this earlier. We were so thankful. That will allow us to has allowed us to start the design and will allow us to start the initial phase of excavation, this initial drift here, starting next year. Ultimately, these caverns, we're hoping up to 2 of them will be funded through a private donor. And that work should have these excavated by 2030, which aligns with the construction schedule for the next generation of dark matter and almost aligns with the neutrino double beta decay experiments that are proposed for the ton scale. We're hoping to attract the beyond ton scale, 100 tons of those hockey pucks, if you want to remember those. So up to 2 caverns, 100 meters long, a little smaller than the LBNF caverns, but this is what the community so far has said will work for their experiments. We'll go back to the community and say, we really mean it, we have the money, we're doing it. Is this the right dimension? Is this the right size? Is this the right configuration? And we'll hear from that community and make sure we're serving their needs. So we're very excited about this. This is amazing. Since this is STEAM, I wanted to go from STEM to STEAM and showcase just in the last slide or two some of our artists, our fine arts endeavors. And one example here, a fabulous example, is our Artist in Residence program. And there was a recent art showing at the University of Michigan. Gina Gibson is our Artist in Residence coordinator. She was our first Artist in Residence. She's a faculty member at Black Hill State University. And she's standing in front of her exhibit. This was work inspired while she was our first Artist in Residence back in 2019, I believe. And so very, very happy to have her helping us engage with the artist community. And we have had Artists in Residence every year since. We also have Neutrino Day. If you haven't heard of Neutrino Day, I'm not sure how we missed you, but it's a free science festival in Lead. second Saturday in July, July 8th. And you can see some of the activities. We have SDPB's Science Steve with all sorts of cool stuff that he does. He's an amazing science communicator. Lots of stuff for kids, and it's a lot of fun. We take over a number of venues and lead the Opera House, the Visitor Center, and we have a lot of fun. The Visitor Center, just to showcase it, it's one of the venues for Neutrino Day, but it's perched right on the edge of the open cut. Fabulous view. Also has a ring from the Ray Davis chamber, looking for the original signals, motivating the neutrino oscillation work that has gone on since. So it's a great facility, tells the science story, but also the mining history story as well. Last thing I want to mention is our new institute. We're standing up an institute for underground science at SURF, and it aims to engage with a number of stakeholders, universities, other underground laboratories around the world. Remember that sprinkling of 18 around the planet. SURF would be a contributor. It's not a SURF-only institute. National laboratories that we partner with, and then other research institutes. So all of these as input to the science that we currently support and hope to promote to thrive at SURF. So this institute did a soft launch, or is doing a soft launch this summer, and one of our first science-specific endeavors is to host a topical workshop on physics, neutrinos and dark matter. And so that's what's going on today. In fact, it started yesterday. I gave a slightly different talk to a group of mostly theorists working on dark matter and neutrinos this morning. This is our conference website talking about the science that is focused on at this workshop called Setup. And they're attracting 70 scientists from all over the world to lead South Dakota to talk about physics. And this is exactly what we want the Institute to do. And we're hoping to make that into a bigger thing, a global thing, in fact. And with that, I will wrap up, and thank you for your attention, and happy to answer any questions. Go for it. Yep.
How are you going to get all that argon out?
That's a good question. And so, oh, yep. How do you get the argon underground? The 13 million gallons of argon. And so first of all, we got to get it to site, get it up to lead. And so while we're filling, if I remember this right, we will have 5 tanker trucks of argon, 5 per day for probably 6 months. So huge logistical, and they've been thinking about logistics for this project for 4 or 5 years. To get it underground, we are putting in a pipe in the shaft. Ultimately, it goes into the detectors and it's cooled to be liquid argon. That's the detector medium that we're interested in. We could send the liquid down the shaft, but the liquid, if a pipe burst, it would expand 700 times and would pose an oxygen deficiency hazard in the shaft. The shaft is our main way of getting in and out. It's a critical part of our safety system. And so we are going to accept the liquid argon on site, boil it, send it down as gas, recondense it, and put it in the detector. So there was a bit more of the story that I wanted to touch on there. But yeah, big pipe in the shaft. So the question is, what temperature do we keep the argon at to keep it liquid? Minus 300 Fahrenheit. Minus 300 Fahrenheit. So a cool day in South Dakota. Other questions? Go for it.
How would you describe your working relationship with School Mine?
Huh? We have a great relationship with School of Mines. They're involved in many of the projects, also on the biology, geology, and engineering side that I didn't speak too much about. And so across the multidisciplinary science program that we have at SURF, they are a main player in many of those experiments. They're members of the LZ collaboration. They're members of the Majorana demonstrator collaboration. They're members of CASPER, in fact, the PIs for CASPER. I am on the physics department's advisory board, and they asked that question as well about how that relationship can be built. Jim Rankin, the president of Mines, is on our board of directors as an ex officio member. So there's, and I could go on. We have members of a science program advisory committee. There are 2 or 3 School of Mines members on that. So very, very close ties at all levels, including evaluating the best science that needs to go into our, or that should go into our facility, that should take advantage of our facility, and that should receive priorities. In terms of untapped potential, it's hard to say. If maybe I'll throw out one thing, if Mines was interested in getting involved in computer science, quantum computing, receiving grants for a dilution refrigerator to move underground, we would love to talk to you, because that is, our director, Mike Headley, has a computer science background. And so he wants the computer science to be one of our science pillars, like physics and biology and engineering and computer science. I'm somewhat tongue-in-cheek there, but the quantum computing has been identified as the coherence of, the decoherence of the qubits is enhanced when you're on the surface and decreases when you're underground. I think there are groups that are interested in doing error correction. In fact, the former chair of the physics department, Andrei Petikoff, is working at Google now, working on quantum computers. And so there are some ties that might blossom in that arena. So that's just one idea.
When you excavate the rock, 800,000 tons of waste rock, somebody an assay to determine whether they gold?
There's no gold in that rock. No, I'm serious. that is a question we get often. We do a sort of an assay. We want to characterize it for the amount of radiation that it will produce, because that will be a background for the LB Neptune experiments and all of the physics experiments. We often get the question, so when you blast all that rock, who's looking for the gold? And there were 7 rock formations that characterized the Homestake site. One of them hosted gold, and it was a thin ribbon that went throughout the underground. And so the rock that we're excavating, all 800,000 tons of it, is called the Poor Man, and it was called the Poor Man for a very good reason. It had absolutely no gold, but great geotechnical properties for huge caverns. Same with the I don't have the full map, but when Ray Davis went to the Homestake Mining Company back in the 1960s, and he said, "Hey, have I got a deal for you? I'm going to look for neutrinos coming from the sun in 100,000 gallons of dry cleaning fluid, and I need an underground level around the 48, 50-foot level." To their credit, the mining company Homestake said, "Sure, let's do that." There's the rock that hosts the Davis cavern is our best rock, I would argue, for these large caverns. It has absolutely no gold, and frankly, that's what Ray would have wanted, because you don't want to be a parasitic physics experiment at that time between a mining company and what they're mining, because you will lose every single day. And so they put him, we're mining over here, Ray, you can go over there, and that worked out perfect. The back. So the question is, we're using the biggest machines, and this is a good picture. We're using some of the biggest mining equipment anywhere in North America. Does that fit on the elevator? And the answer is no. And so you absolutely have to, and this is what they have to do at other mines as well, but you have to cut this into pieces. Often there'll be strategic points on this machinery, basically a sign that says cut here, and then they either bolt it or weld it back together underground. It's part of the mobilization and demobilization. The elevator for bringing equipment underground is 12 feet by 4.5 feet by 12 feet tall. Everything underground has to fit in that. And so when I mentioned earlier, building a ship in a bottle, everything has to go down. Sometimes we'll bring components down slung underneath the cage. And so a good example would be, let me show back up here. Oops, yeah, we don't need to do that. See if I had the picture. Yeah, maybe I don't have that picture. It's in the video. Those large beams, the 6 million pounds of large beams for the exoskeleton for the cryostats, each of those is about 50 feet long. It has it has a special attachment at the end of the rope that normally would hold an elevator chamber. We're going to take that elevator chamber off and attach these beams to that rope. And then as you can picture, you're coming down the shaft, you're at the end of the rope, and then you have to attach another rope to pull that beam out onto the level. And there are hundreds of those beams. And that's, that presented some challenges. We actually have to blast out the interface between the vertical shaft where it meets the horizontal level. That curve needs to be higher than it is now to bring out these long beams. They were able to bring that other machinery down, breaking it up into, I don't know, 3 or 4, or probably even more pieces in some cases. The tires for some of those pieces of equipment are yay tall, like they're huge. But that mining companies are very good at that, and we just stand out of their way and let them do their thing. That's a good question.
So if that equipment is kind of how you have to take it apart,
I think in many cases it is. It may be some of the older equipment that we have to actually cut with a torch and weld back together. I think a lot of these newer pieces are exactly the way you described. They're modular, so it's intended to be plug and play to a certain extent. Oh, you're taking a picture? Other questions? There's a lot of good questions that came up. All right. Well, with that, I'll thank you for your attention. Thank you.
Thanks again for coming. Like I said, we do this every third Tuesday. So next month, it'll be July 18th is the third Tuesday. And next month's presentation is actually a panel discussion on critical minerals. We will be hearing from 2 of our faculty members, 2 undergraduates, and Jason Combs, who's the program director of the National Security Innovation Network. They're going to discuss current shortages of critical minerals, how that's going to affect all of us in here today, future generations, and what the university is doing to try to combat that. So hope to see you next month.